Welcome to the deep dive. Today, we're cutting through all the noise to get to what is really the most fundamental building block of modern cloud infrastructure.
That's right. For anyone who follows this space, we talk a lot about Kubernetes, about pods and deployments, but today we're taking a step back.
A required detour, you could say.
Yeah, exactly. Because before you can manage thousands of applications, you have to understand the one piece of cargo those systems are built to manage, the container.
We've spent so much time on the complex symphony of Kubernetes, the scheduling, the scaling, the whole orchestra. But if the application is the main instrument, we really need to know how that instrument is built.
And that's our mission today. We're going to strip away the buzzwords and just get to the source. What is a container? What makes it so different from, say, a VM? And this is the crucial part. How did standardization make it possible for any container to run, well, anywhere?
That last part feels like the secret sauce that makes the whole thing work.
It really is. It's the quiet powerhouse behind everything.
Okay, let's unpack it. Where do we start? The absolute bare minimum definition. What are the two key ideas a container gives us?
It's all about isolation and portability. If you remember nothing else, remember those two words.
Isolation and portability. Okay, what does that actually mean for a developer in their day-to-day work?
It means we finally solved, the oldest and most frustrating problem in software history.
Don't say it.
It worked on my machine.
Ah, yes.
The classic.
A container solves that by bundling absolutely everything an application needs into one neat package. I'm talking about the code, the config files, the libraries, every single dependency.
I have vivid memories of the dark days before this. You'd spend a week debugging a production deployment just to find out the server had, Python 3.7, but your laptop was on 3.8.
A total nightmare. And that's the beauty of it. The container carries its own environment with it. So the host server's operating system just becomes a platform. The application inside never worries about version mismatches because it brought its own. So we have this isolated, portable, self-contained little bundle. This immediately brings up the biggest point of confusion for anyone new to this space.
I know where you're going with this.
How is this different from a virtual machine, a VM?
Right. And getting this difference is the key to understanding why containers are so much more efficient. Do you think VM, you start with physical hardware, right?
Yeah, the bare metal.
On top of that, you install a hypervisor.
Which manages the virtualization.
Exactly. But here's the critical difference. Every single VM needs its own full copy of an operating system, the guest OS. So if you have 5 apps,
you need 5 hypervisors and 5 separate operating systems all running at once, all eating up CPU memory.
All of it. They're inherently heavyweight, they're big, they're cumbersome, and startup times are measured in minutes because you have to boot a whole OS every time.
Okay, so that's the VM. Now compare that to the container. How does it get away with being so much lighter?
Containers just ditch the guest OS entirely.
They just don't have one.
They don't need one. They share the host operating system's kernel. They only virtualize the application layer. Instead of running a full Linux OS, for example, they just use these powerful features built right into the host kernel.
And these are things like Linux namespaces and control groups.
You got it. C groups. That is the technical secret sauce. Namespaces provide the isolation. They trick the container into thinking it has its own private file system, its own network, its own process IDs.
Even though it's sharing the real ones underneath.
And C groups handle the resource management. They make sure one container can't just hog all the CPU and memory. It prevents that noisy neighbor problem.
That sounds incredibly efficient. But if they're all sharing the same host kernel, doesn't that create a security risk compared to a VM, which has a totally separate OS?
That is an excellent question. And it really hits on the core trade-off. You're right. A VM offers true hard separation because the guest OS is completely separate, often down to the hardware instruction level.
Total isolation.
Right. Containers rely on that shared kernel, which means it's a single point of failure. If there's a serious flaw in the host kernel, or if an attacker manages a container breakout.
They could potentially get access to the host or to other containers on that host.
Potentially, yes.
Yeah.
The security is at the application level, not the full OS level like a VM. That lighter isolation is the price you pay for that massive gain in efficiency.
Okay, that context is vital. So if a VM is like building a whole independent house for your app with its own foundation, plumbing, everything,
then the container is like a secure, self-contained apartment in a big building. Your apartment has all its own furniture, the dependencies, but everyone shares the building's core infrastructure, the plumbing, the electricity, That's the host kernel.
You save a ton of resources, but you're all trusting the integrity of the building.
Perfectly put.
Okay, so we've nailed the difference between the running environment, the container, and the VM. Let's shift from the running thing to the thing we actually build and ship around. The relationship between a container image and a container.
Simple analogy. The image is the blueprint. The container is the running house built from that blueprint.
And what's the most important characteristic of that blueprint, that image?
It is immutable, read-only. It's a static file that you build once, and then you store it in a container registry, which is just a big digital library for these blueprints.
And immutability is a huge...
Oh, it's enforced aggressively.
Yeah.
If you start a container from an image and then, say, you SSH in and install some tool or change a config file,
Yeah.
those changes only exist in a temporary writable top layer. The second that container stops, poof, they're gone.
Yeah.
Unless you explicitly save those changes as a brand new image.
Which gives you consistency. You always know the image you tested in staging is the exact same one running in production. No drift.
And that consistency is possible because of a really smart design choice. Layering. Images are built in layers.
Let's spend a second on layering, because this is where the huge speed boost for CI/CD pipelines comes from.
Right, so think of your Docker file, your image definition. Every instruction install a base OS, add a framework like Node.js, copy your own code. Each of those creates a separate read-only layer. They stack on top of each other.
So you have your base Linux layer, then maybe a Python layer, and then your app code on the very top.
Exactly.
So what happens if I just change 2 lines in my application code, that's just that tiny top layer?
When you rebuild, that's the only thing that gets rebuilt. The heavy lower layers, the gigabytes of OS and Python, are already cached. They don't change. And when you push that new image to the registry, you're only uploading the tiny new layer.
Which means faster builds, way less network traffic, and quicker deployments. That saves real time and real money.
It's absolutely foundational to how modern software is delivered.
Okay. We have the blueprint, the image, we have the running instance, the container. We need an engine, the actual software that takes the blueprint and brings it to life. What is that piece?
That is the Container Runtime. It's the low-level engine that does the work. Its job is to pull the image, use the kernel's groups and namespaces to create that isolated environment and start the process.
Now, most people have probably heard the name Docker. The Docker engine is what made all of this famous. But in the world of Kubernetes, you hear different names like Containered or CRIO. What's the deal there?
This is a really important part of the story. The original Docker engine was monolithic. It did everything, building images, storing them, running them.
For jack of all trades.
Right. But when Kubernetes came along, it didn't need all that. It just needed one simple capability. Run this container. The rest was just extra complexity and overhead.
And this is what led to the whole deprecation of the Docker shim, right?
Exactly. Kubernetes standardized the way it talks to runtimes using something called the CRI, the Container Runtime Interface. This allowed it to talk directly to leaner, more focused runtimes like Containered or CRO, which do one thing really well, run containers.
So the kubelet on a worker node just talks to the CRI, and the CRI tells Container, go run this image.
Yep, it's cleaner, faster, and much more streamlined.
That whole move towards a standard interface is the perfect setup for our last topic. If you have different tools building images, different systems managing them, and different runtimes executing them, how on earth do they all speak the same language?
You are hitting on probably the biggest and quietest success story in all of open source infrastructure.
Which is?
The Open Container Initiative, or OCI.
The OCI, that's the standardization glue that holds all this together.
Absolutely. The OCI was created specifically to make sure the container world didn't splinter into a bunch of proprietary, incompatible formats.
A format war.
Nobody wanted that. So
Right.
they created standards for the 2 most important things. First, the image specification. It defines exactly how a container blueprint is packaged and layered.
So every build tool creates the same kind of artifact.
Correct. And second, the runtime specification. This defines exactly how an engine must set up and run a container. So Kubernetes knows precisely how to talk to any runtime that follows the spec.
So because of the OCI, I can use Docker to build an image, push it to a registry from a totally different company, and then have Kubernetes use a runtime like CRIO to pull and run it, and it all just works.
That's the whole point. Universal compatibility. It prevents vendor lock-in and lets the whole ecosystem thrive.
This has been a fantastic deep dive. Let's try and synthesize the 3 biggest takeaways for everyone listening.
Okay. First, containers give you portability and isolation by cleverly using host kernel features like namespaces and key groups, making them way more efficient than heavyweight VMs.
Right. Second, the container image is your immutable blueprint, and its layering is the key to fast, efficient builds and deployments in any modern pipeline.
And third, the OCI, the Open Container Initiative, provides the critical standards for images and runtimes. It's the universal translator that allows all these different tools from different vendors to work together seamlessly.
So if the container is the perfectly standardized package, the OCI is the universal barcode and shipping label that lets the delivery system Kubernetes handle it anywhere in the world.
It's a beautiful example of how good standards drive innovation. Because the basics are agreed upon, companies now have to compete on making better tools and faster runtimes, not on locking you into their format.
Okay, now here's a final thought for you to take away. The cloud-native community pulled off something incredible. They standardized the fundamental way we package and run software. This success freed up developers to just focus on building things faster. So if we applied that same model, a vendor-neutral body defining the core interfaces, to other complex, siloed parts of infrastructure, like data storage protocols or maybe serverless function APIs, what kind of revolutionary jump in speed and agility could we see next?
Just think about the power of those universal non-proprietary standards.